So now we're in week 3, and this week's topic is going to be understanding backpropagation and neural networks, a deeper dive. We're going to be exploring how neural networks learn and adapt. So, we're going to be diving into mechanics behind neural networks. We're also going to be focusing on the backpropagation algorithm. We're going to be exploring how backpropagation improves models like large language transformers, and we're also going to be breaking down the math behind neural network learning. So, let's start with the basics of neural network. Imagine we have a very simple network with one neuron in each layer. Each neuron has a weight and a base. We'll use 3 weights and 3 bases to keep things straightforward. Our objective is to understand how sensitive the cost function is to change in these weights and bases. This sensitivity is crucial because it helps figure out how to adjust these parameters during training to minimize the errors. So, the cost function. As you can see here, this is the formula for the cost function. Let's consider one training example. The cost function, denoted as C0, measures how far the model's predicted output of A over L is from the actual target of value Y. The simplest form of the cost function is the squared error, which can be expressed as this formula right here. When A over L is the activation of the final layer and Y is the true target, this tells us how the well network performed for a particular example. By minimizing this cost, we can make the model's prediction more accurate. Next, we go into the sensitivity calculation. Now we need to understand how sensitive cost function is to the changes in weights. Imagine that we tweak one of the weights just a little. What happens to the output of A over L and the overall cost? Essentially, we want to calculate the derivative of the cost function with respect to each weight. This derivative tells us how much the cost will change if we make a small adjustment to a weight or basis. This sensitivity is what guides the learning process during training. By applying the chain rule, you can see that it helps compute how the cost function changes step by step. You can see on step 1 how Z over L changes with respect to W over L. Then we go into straight to step 2, how A of L changes with respect to Z over L. And step 3 on how C changes with respect from A over L. When we calculate how the cost function C changes when you respect to A over L, the derivative of the cost function with respect to activation tells us how much of the output is affecting over the overall cost. Now we're gonna be looking at derivatives of key terms. The derivative of cost function C with respect is on this formula. This shows that if the prediction output is far from the target, Y small changes in weights will have a significant impact on the cost. The derivative of activation with respect to the weight sum will be this equation, depending on the type of activation function used. And now, the derivative of weight sum with respect to the weight of W over L is simply the activation from the previous layer, which is A over L minus 1, because the weight sum is a linear combination of the previous layer's outputs and weights. Now, for the next slide. So, next, once we have these derivatives, we can use them to adjust the weights and biases. For each training example, we compute the necessary adjustments to the weights and biases to minimize the overall cost function. This process is known as backpropagation. Starting from the final layer, we propagate the error backwards through the network, adjusting the weights at each layer based on how sensitive they are to the error. This allows us to update the model step by step, gradually minimizing the cost. Next, we're going to be talking about extending the multiple neurons. Now, things get a little more complex when adding more neurons in each layer. With multiple neurons, we have more weights and activations to consider. But the core idea remains the same. We calculate the cost for each neuron and sum them up to compute the total cost. We use subscripts to track each weight and neuron's contribution to the cost. This gives us more nuanced understanding of how each part of the network contributes to the final output. Repeating the process. Backpropagation is not a one-time process. We repeat it for every training example in the dataset. After processing all examples, we average the adjustment made to the weights and bases. This averaging helps ensure that the model generalizes well to unseen data. If we only focus on one example at a time, we might end up overfitting the model to the particular example, leading to poor performance on new data. Next, we're going to be talking about stochastic gradient descent, or SGD. To speed up the training, we don't process all training examples at once. Instead, we use a technique called SGD, where we process the training examples in mini batches. This speeds up the computation by updating the weights more frequently, and through the gradients may be less precise. It helps the model scale to a much larger data set. Now, the final thoughts on backpropagation. At first glance, backpropagation may seem like a complicated process, but it's really the backbone of neural network training. By calculating the gradients for each weight and bases and adjusting them accordingly, we can gradually minimize the cost function, and this allows models to make more accurate predictions over time. As training progresses, the network gets better and better at understanding the relationship between input and output. Next, we're going to be talking about connecting backpropagation to language models. Now, let's take a step back and think about how this all fits into a larger model like ChatGPT. These large language models, such as transformers, use backpropagation to refine their parameters. Essentially, these models learn how to predict the next word or phrase based on the context. They do this by processing vast amounts of text and adjusting the parameters through backpropagation, improving their predictions over time. Now, next slide, we're going to be the role of attention mechanisms. Transformers take things even further with something called attention mechanisms. This allows the model to focus on different parts of the input depending on the context. For example, in a sentence, the model can pay more attention to certain words based on their relevance to others. This makes transformers much better at understanding context and generating more accurate human-like responses. Lastly, we're going to be going over large-scale computation and GPT's learning process. Training these models requires immense computation power. We typically use GPUs to handle the mass amount of data computations required. These models are pre-trained on large datasets and later fine-tuned using techniques like reinforcement learning with human feedback. This fine-tuning process is key to improving their ability to generate responses that feel more natural and human-like.